Hello and welcome. This is Dr. Jeremy Mandelkern of drmtutoring.com, and today we're going to be looking at evaluating limits algebraically. If you like this video, feel free to click on the like button. You can also comment in the comment section and share the video with friends or classmates if you feel it would be helpful to them. There are also worksheets in the intro video, including this one. So I've written here some helpful key ideas that we can be using today when evaluating limits algebraically. The first idea here is that when things don't go according to plan, if we get an indeterminate form and we don't know what the value of the limit is immediately, we might try factoring or using the conjugate or other algebraic simplifying methods. We also don't want to forget our factoring formulas, like the difference of squares factoring recipe, the difference of cubes factoring recipe, etc. And conjugates can be useful sometimes when evaluating limits algebraically. There are some limit rules that are given in the worksheet. They are fairly intuitive, stating, for instance, that a limit applies across a sum or a difference, provided that the individual limits exist. Same thing goes with a product. Same thing goes with a quotient, provided that the limit of the denominator is not 0, and also a limit of an nth root of a function. Provided that the limit of the radicand exists, we can pass the limit inside the root. That is a useful property. So here, we're going to dive in. The first thing I like to do when evaluating a limit algebraically is to check whether, for the case of rational functions, whether the function is defined at the value for the variable that we're taking the limit of. In this case, it's a limit as y goes to 2. Is the function defined at 2? Well, it is. And because the function is defined at 2, we can actually evaluate this limit directly by evaluating the function. So in this particular case, the value of the limit is 0. The denominator is observantly non-zero when y goes to 2. A rule of thumb with rational functions is if you're taking a limit towards a value for the independent variable where the function is defined, then the limit will be the function value. Okay, that is a rule of thumb. Here, put another way, where the function is continuous, the limit will be the function value, and rational functions are continuous on their domain. Let's try the next one. If we try the same technique as we used in the last problem, just sticking in 2 for y, as in here, sticking in 4 for x, we get into trouble. Why are we in trouble? Well, we can see that we're getting an indeterminate form, okay? The notation for this indeterminate form might be written as like a 0 over 0. And what that means is in the suggested limit, as x goes to 4, we're finding that the numerator is racing to 0, as is the denominator. So who's going to win the race? So to find out, we should try one of the key ideas, which is factoring. Here in the numerator, we can see that that is a difference of squares. So let's go ahead and write the limit, but with the numerator factored. So x squared minus 16 factors into x minus 4 times x plus 4. And in the denominator, we still have what is x minus 4. And we'll see if we can draw that line just a little bit better. Well, they say the third try is the charm. Now we can go ahead and observe that there is a common factor of x minus 4. We could and we should cancel out this common factor. So here we can go ahead and just say that that one and that one cancel out. And what remains in the numerator is a polynomial function. Polynomial functions being so well behaved, we can evaluate limits of them directly by just plugging in what is the value, in this case 4, in for x. So we get 4 plus 4, which is 8. In this next problem, we see that we're taking the limit as y goes to 4 of some quotient function that is not a rational function. So we're going to try to use an algebraic technique here. The technique to use in this particular case is the conjugate. So we're going to multiply the denominator by essentially what looks like the same expression, but with a plus symbol in the middle. And we'll also do the same with the numerator, multiplying the numerator by the conjugate of the denominator. So why do we do this? Well, the reason being is that we can simplify the product in the denominator. So applying now what is like the FOIL method of multiplication, we can see that the multiplication in the denominator has simplified a little bit. So in particular, we are finding the following. So we have 2 times 2 is a 4. 2 times a root y, well, wait a sec. We also get minus 2 times root y. So those terms are canceling. We have a minus root y squared, which is minus y. In the numerator, we already have a factor of 4 minus y times that conjugate factor, which is 2 plus root y. So once again, we see that we can cancel essentially what is the troublemaking factor that's producing the 0 in the bottom. So we'll go ahead and do this. This is canceling to make a factor of 1 then. And we can apply the limit to the remaining expression, the simplified expression. So here, the limit as y goes to 4 of just 2 plus root y is going to be 2 plus the square root of 4, which is 2 plus 2, which in turn is 4. And there we've solved that limit problem. Let's try the next one. So in the next one, here we have the limit as x goes to 1 of, another rational function. So the first thing we want to check is we're approaching 1, that is, x is approaching 1. Is the function defined at 1? Okay, it is not. So this function has some bad behavior going on at x is equal to 1. Either we have an asymptote or a hole, perhaps. So we'll observe that in the limit as x goes to 1, the numerator is approaching 0, as is the denominator. So we can write that symbol 0 over 0 to indicate that this is an indeterminate form of this type. And we'll try this time using difference of squares. We'd used it previously, so let's try it again. Surely the numerator is a difference of squares, so this could be applicable. In the numerator, we have x squared minus 1 times x squared plus 1. And in the denominator, there is the same factor of x minus 1. So we'll go ahead and observe now that there's further factoring that can be done in the numerator. When the dust settles and the smoke clears, let's do the division bar first. It's going to be pretty long, so that should be sufficient. And in the top, there is x minus 1 times x plus 1. We are factoring x squared minus 1, and there's still the factor of x squared plus 1. In the denominator, we have x minus 1, and there is a common factor here. It is x minus 1. So we can go ahead and divide it out. In the numerator, we just have the product of those two factors, x plus 1 and x squared plus 1. And most importantly, that is a polynomial function, so the limit will be the function value. Since polynomial functions have this property that everywhere, the limit of them is their function value. So we have what is 1 plus 1 times 1 squared plus 1. When the dust settles and the smoke clears, this is going to be 2 times 2. So we have the value 4. And in our last example today, we have a quotient function that is not rational. It has a root in it, When we try to pass x to 0, the denominator clearly is going to 0. That is bad news for us. The numerator is also going to 0. That doesn't mean necessarily that the limit does not exist. More work is needed to find out. So we can go ahead and indicate this. So we have the form for the indeterminate expression is 0 over 0. Numerator is racing to 0 in this limit, so is the denominator. Who will win? Let's go ahead and try once more the conjugate. This time we'll multiply top by the conjugate of the numerator expression, which will be looking pretty much the same, but we'll change the sign in the middle. So here we have 3x plus 16 plus 4. And we'll multiply the denominator also by this factor. And it's not guaranteed to work, but it seems like a pretty good idea. And when we multiply out now in the numerator, since we haven't taken the limit yet, we must continue to write it. We'll now do what is the FOIL multiplication. So multiplying out the two binomial expressions, two-term expressions, we find in the top that when you multiply the root expression by itself, we get just the radicand, so just 3x plus 16. There are opposite terms now generated. The outside and inside products are opposites of one another. They are plus or minus 4 times the root expression, so they cancel. And the last product is minus 16. Well, that's kind of nice, isn't it? In the denominator, we have x times this same nasty conjugate factor. And clearly, we see there's more simplification now because the plus 16 and the minus 16, they are canceling. So these two cancel. And we can go ahead and divide out what is the x. So since after canceling the plus and minus 16, it's just a monomial 3x in the top. There's a factor of x clearly there, as there is a factor of x in the bottom. So we finish the problem by applying the limit to what is the simplified result. There is no x's left in the numerator, so there is a 3 in the top. And in the bottom, well, we'll plug in what is 0 in for x, and we get what is a root of 0 plus 16, which is 4, plus another 4. So we get 3/8. So here we have finished yet another worksheet, a calculus worksheet on limits algebraically. I hope you enjoyed this video and found it instructive. If you liked the video, remember to click like. You can share the video with friends or classmates, and you can subscribe to the channel as well. I look forward to meeting you for future worksheets. In our next calculus video, we're going to be looking at the topic of continuity. Thanks for coming, and bye-bye.